In this video, we will learn about the different types of mixtures. Some mixtures you may be familiar with are milk, orange juice, blood, air, mayonnaise, soil, and metal alloys. We will spend most of our time together here on solution mixtures specifically. Let's start by having a look at what a mixture is and comparing them with things that are not mixtures. All matter can be placed into two groups, the pure substances and mixtures. Pure substances can be further divided into the elements, for example lead, oxygen, argon, and chlorine, and the compounds, for example water, carbon dioxide, and CaCl2, which is calcium chloride. A compound is a substance made of two or more different elements chemically bonded together. Mixtures, on the other hand, are composed of two or more different substances not chemically joined or bonded together. The definitions seem similar at first glance, but are actually very different. In compounds, the elements are chemically bonded, but in mixtures, the substances, whether elements or compounds, are not bonded. Examples of mixtures include salt water, which is sodium chloride in water. Sodium chloride is a compound, and water is a compound. So salt water is a mixture of two compounds. Air is another example of a mixture. It contains the elements nitrogen, oxygen, argon and other noble gases, and some compounds such as carbon dioxide and water vapor. So air is an example of a mixture composed of elements mixed with compounds. So far we have briefly recapped elements, compounds and mixtures, which you can learn more about in another video. Now let's turn our attention specifically to mixtures. Types of mixtures. Mixtures can be described as being either homogeneous or heterogeneous, occasionally referred to as homogeneous or heterogeneous. The prefix homo means same. The prefix hetero means different. So a homogeneous mixture is one with a uniform or same composition and properties throughout the mixture, but a heterogeneous mixture is a mixture with non-uniform or different properties and composition at different places in the mixture. Notice the even distribution of the different particles in a homogeneous mixture and the uneven distribution of the different particles in a heterogeneous mixture. Let's look at some specific examples. If some orange food coloring were added dropwise to water and mixed thoroughly, the particles would distribute themselves evenly throughout the mixture. Every part of the mixture would look the same and have the same properties. It is difficult to draw this. Here it looks like there are visible particles, but in reality in a homogeneous mixture, the individual particles of the different components are not visible to the naked eye. It is more accurate to draw the picture like this. Another example of a homogeneous mixture is when sodium chloride or table salt is added to and dissolved in water. The sodium and chloride ions disperse evenly throughout the water. To draw this more accurately, we would draw the mixture without any distinguishable visible particles. What about examples of heterogeneous mixtures? When oil and water are added together, distinct layers form. The less dense oil floats on top of the more dense water. The composition and properties of the upper oil layer differ from the composition and properties of the lower water layer. The two different components are clearly visible. When chalk powder is added to water and stirred vigorously, dissolution or dissolving does not occur. The individual chalk particles are clearly visible in the water. After some time, the chalk particles begin to settle. There is a very evident uneven distribution of components, and properties are not the same throughout this mixture. Samples taken from different places of a heterogeneous mixture would be quite different. while samples taken from different places in a homogeneous mixture would be the same. Now, one type of homogeneous mixture is a solution. A solution consists of a solute in a smaller proportion or a smaller amount mixed uniformly in a solvent, which is present in a larger proportion or a larger amount. Using the example we used a few moments ago, sodium chloride would be the solute, present in a smaller amount, and water the solvent, present in a larger amount or a larger proportion. And when mixed together and dissolved in each other, the ions of the solute become evenly dispersed in the solvent, forming a solution. In this case, a salt water solution. The solvent and solute particles in a solution are often similar in size. Two types of liquid-based heterogeneous mixtures are the colloids and the suspensions. A colloid consists of fine particles, usually large molecules, dispersed but not dissolved in another substance. An example of a colloid is milk. In a colloid, the component in the larger proportion is called the continuous phase, and sometimes called the dispersing medium. The dispersed particles are called the dispersed phase. In milk, the dispersed phase is composed largely of tiny oil droplets. Sometimes these are visible to the naked eye when you look closely at milk, but sometimes they are not. A colloid can look rather homogeneous, but on very close inspection, or with a magnifying glass and sometimes with a microscope, you can see the individual dispersed particles. This is not possible in the case of a solution. Another example of a colloid that we are familiar with is fabric softeners. A suspension contains even larger particles than that of a colloid. They do not dissolve but remain suspended in the liquid and over time settle out to the bottom of the container. An example of a suspension is sulfur powder suspended in water, or chalk powder, or even baking flour. Over time, the sulfur particles begin to sink to the bottom of the vessel. When everything has settled out, we refer to the solid as a precipitate. Moving from a solution to a colloid, and from a colloid to a suspension, we see decreasing homogeneity. In other words, solutions are the most homogeneous, and of the three, suspensions are the least homogeneous, or the most heterogeneous. Now, solutions, colloids, and suspensions often have a liquid for their main component, but this is not always the case. Let's investigate solutions specifically, and we will see that the major component is not necessarily always a liquid. We know that solutions consist of a solvent, which is the component present in the larger proportion, and a solute, which is the component present in a smaller proportion, dissolved in the solvent. Now, the solvent can be in the form of a gas, a liquid, or a solid, giving the overall form or appearance of the solution as a gas, liquid, or solid. Solutes can be gaseous, dissolved in a gaseous solvent, or a gas dissolved in a liquid, or a liquid dissolved in a liquid, and what is most familiar to us is when solids are dissolved in liquids. Similarly, the solute in a solid solution can be a gas, a liquid, or even a solid. Let's look at some examples. Air is an example of gases dissolved or mixed homogeneously in gases. The propane-butane mixture in Bunsen burner fuel is another example of gases mixed homogeneously with other gases. An example of a gaseous solute in a liquid solvent are carbonated soft drinks or sodas. These beverages contain dissolved carbon dioxide gas. Ethanol in alcoholic drinks such as wine and beer is an example of a liquid solute dissolved in a liquid. We've seen that salt water is a classic example of a liquid solvent contain dissolve in it a solid solute. Other examples are sugar water and black coffee. What about solid solutions? An interesting example of a gas dissolved in a solid. Hydrogen dissolves excellently in palladium. This kind of system is a way in which to store hydrogen. Hydrogen has many potential uses, one of them being use as a fuel in place of fossil fuels. Dental fillings used to routinely be made from liquid mercury dissolved in solid silver, tin, and copper amalgams. However, this practice in dentistry is less common than before because of the toxicity of mercury. Lastly, an example of a solid dissolved in a solid are alloys. For example, steel, which is composed largely of carbon dissolved in iron, and brass, an alloy of copper and zinc dissolved in each other. They are dissolved in each other in the liquid form, and when cooled, they solidify into a solid form. Now we know that solutions can be of different types or different forms, depending on the form of the solvent and solute. Now let's investigate a different way to describe a solution based on the amount of solute dissolved in the solvent. We will use the example of a solid solute dissolved in a liquid, although what we are about to do can apply to any of the solutions on this table. The proportion of a solute dissolved in a solvent can be changed. If a small amount of solute is added to a solvent, it will dissolve. We call this an unsaturated solution. If more solute can still be added and dissolved. In other words, if the maximum capacity of dissolved solute has not yet been reached. If we add more solute and dissolve it, and we continue doing this, the solution will become more and more concentrated. A point will be reached where the solution contains the maximum amount of dissolved solute. It cannot dissolve any more. We call this a saturated solution. A saturated solution is a solution which contains the maximum amount of dissolved solute at a certain temperature. We will not go into depth of the effect of temperature in this video, except to say that usually the higher the temperature, the more solid solute can dissolve. The last scenario is one in which more solute is added. We can get the solute to dissolve if we heat the solution. We can then let the solution cool back down to its original temperature. The solution is super concentrated. We call it a supersaturated solution. A supersaturated solution is one which contains more dissolved solute than it usually can under normal conditions. Supersaturated solutions are usually not stable. Any disturbance to a supersaturated solution, such as vibrations or dust particles entering the solution, may cause the extra or excess dissolved solute to precipitate out of solution, forming solid particles which sink to the bottom of the vessel. We now know that solutions are composed of solutes and solvents dissolved in each other. They are homogeneous and can be unsaturated, saturated, or supersaturated. Let's look at one last specific type of solution, and that is those that conduct electricity. Solutions which can conduct electricity contain either an ionic compound or a polar compound. We call these compounds electrolytes. Electrolytes are polar or ionic substances which dissociate or ionize into cations and anions when dissolved in solution and can therefore conduct electrical charge. A strong electrolyte will ionize or dissociate completely, while a weak electrolyte only ionizes partially. Hydrogen chloride gas, which is a polar compound, when it reacts with water, it forms the H3O plus ion and the chloride minus ion. We say it ionizes completely because all of the hydrogen chloride is converted to product. Ionic sodium chloride, when it comes into contact with water and dissolves in water, it dissociates to form sodium ions and chloride ions. the dissociation is complete, meaning that all of the sodium chloride is converted to product or to ions. So strong electrolytes form many ions in solution. Acetic acid, whose IUPAC name is ethanoic acid, is a weak electrolyte. When it reacts with water, it forms the acetate ion and the hydronium ion, but only to a small degree. The equilibrium arrow shows that some of the product is reconverted back into reactant. For weak electrolytes, fewer ions form in solution. Because strong electrolytes form many ions in solution, they are very good conductors of electricity. And weak electrolytes are poorer conductors of electricity. A non-electrolyte is a compound which cannot form ions in solution and therefore cannot conduct electricity. An example is sugar. Molten electrolytes also conduct electricity. These are not technically solutions, though. They are not composed of solutes and solvents, but merely the molten or liquid state of an ionic compound. Now it's time to summarize everything we've learned about mixtures. We learned that a mixture consists of two or more different substances mixed together but not chemically bonded. Because no chemical bonds need to be broken, the components can be easily separated by physical means. We saw that mixtures can be described as being homogeneous or heterogeneous. Homogeneous mixtures have a uniform composition and properties throughout. And we saw that solutions are examples of homogeneous mixtures. Heterogeneous mixtures, on the other hand, have non-uniform composition and properties throughout. The examples we looked at were colloids and suspensions. We saw that there are many types of solutions, depending on the state of the solvent and solute, and that solutions can be unsaturated, saturated, or supersaturated, depending on the amount of dissolved solute. And lastly, we looked at a specific type of solution called an electrolyte solution, which contains cations and anions capable of conducting electrical charge.